Everyone, my name is Pragya Mishra, of student of BSc third year, and today's topic for discussion is a field extension, finite extension. Then field of any algebraic structure f comma plus comma dot is called a field if it is a commutative ring with unit having multiplicative inverse of every non-zero element of it. For example, q plus dot and r plus dot c plus dot are example of field. Then subfield and subfield is a any non-empty subset S of a field F is called subfield for of it if s comma plus comma dot is also a field. For example, set of real number is a subfield c comma plus comma dot where c is a complex number. Then a theorem: the necessary and sufficient condition for a non-empty subset S of a field F to be its subfield are uh, for for all belongs to a comma b s and a minus b belongs to s, for all belongs to a comma b to s and a comma b inverse to s. Then characteristic of field: for any field f the least positive integer n for which n comma e equals to 0 where e is a multiplicative identity of field is called characteristic of field. Then theorem: the characteristic the characteristic of a field is either 0 or a prime integer. Then proof: by definition of n is the characteristic of field f, then n e equals to 0 where e is a unit element of f. Okay. F if order of e is a infinite, then e comma n n e equals to 0 where n equals to 0. So the characteristic because 0, but if order of e is finite, so n is not equal to 0. Now to show that n must be prime, let if possible n equals to n1, but n1 is not equal to n and n2 is not equal to n1. By n e equals to 0, then n1 in n1 n2 e equals to 0 where n1 e and n2 e equals to 0, then n1 equals to 0 or n2 equals to 0. It is possible for n is least positive integer such that n equals to 0, n is a prime. Then modular field with non-zero characteristic are known as modular field. Uh, Note: a characteristic of a field is equal to characteristic of its subfield. Then field extension. Uh, Let F be a subfield of field K, then field K is called an extension of field F. For example, S Q plus dot is subfield of R comma plus comma dot. So R plus dot is an extension of Q plus dot. Then degree of field: we know that every field from an vector space over its subfield, hence Kf will be a vector space if K is field extension of F. A dimension of vector space Kf is called degree of K over F. it's denoted by k ratio f. Finite extension: if degree of a field extension is finite, then it is called finite extension. Otherwise, it will be an infinite extension. For that, for extension k of field f is k raised to f equals to finite, it will be finite extension, and for k raised to f equals to infinite, it will be infinite extension. For example, c raised to r equals to 2, as c is an extension of r. So CR is a vector space and its basis will be 1 comma I, and the dimension of CR is 2. CR raised to 2. Then some points. Uh, if K is a finite field extension of F and L is finite field extension of K, then L is a finite extension of F and this result. Then if L is a finite extension of a field F and K is a subfield of L containing F, then K raised to F and slash L raised to F. Thank you. Thank you so much.